Okay, this is chapter 9, reservoir analysis and flow duration curve. So the content for this chapter would be just an introduction on surface water used for basically for supply. Okay, and then reservoir design, zones of storage. Okay, mass curve method, which is used to calculate storage, and flow duration curve. Okay, just a recap. So you should know by now that, of course, in hydrology, there is rainfall, and rainfall will produce some surface water. Okay, so surface water is water above Earth's surface, such as in river, creek, lake, and wetland. Before, we always hear about runoff. Okay, but this is more on surface water and the use of this surface water for water supply, okay, for the consumption of us human. Okay, so besides surface water, there are groundwater, okay, which provides the base for surface water called base flow. Okay, this is mentioned a lot in previous chapters, base flow and groundwater. What else? Surface water can be contaminated, okay, by rainwater runoff from homes, roads, lawns, and garden. So here, the main thing is if you have development of houses, roads, so it may be contaminated due to due to human activities and structures. Okay, and surface water supply can be found over the land in stream, lakes, and reservoir. So for this chapter, it's more on surface water supply, okay, on water supply. So it can be found in, usually we take water supply from streams, lakes, and even reservoir. So the most important source of fresh water supply are usually from reservoir, lakes, and stream. Stream is river. Okay, stream is the same as river. If river discharges are constant in time, so surface water resources is simple. Okay, if river flow or discharge are constant in time, but it is not. Okay, you have sometimes we have high flow, sometimes we have low flow. Okay, so in if it's constant, okay, if the river discharge is the same amount, so there will not there will be the need to have a reservoir. Okay, but unfortunate river flow are stochastic in nature. So stochastic means it have a random probability distribution pattern, or we can say that it changes over time. Okay, okay, here change over time means variable with time. Okay, therefore, how to meet the demand from the variable source, okay, a river. So that is why we need reservoir, okay, macam takungan, air takungan. So we need reservoir, okay, essentially to take care of fluctuations in the demand, okay, demand, and also the supply of water. Okay, demand is different, supply is different. Demand is how much water is needed by the people. Okay, supply is how much water exists and available. So we need to find a balance between demand and supply. So typical variation in demand for water in an urban community during a 24-hour period could be relatively high demand in the early hours of the morning, and in the evening, and little demand during daytime. This means like afternoon. Okay. Macam kita lah, pagi-pagi bangun mandi kan, petang malam mandi. Jadi bila yang demand paling tinggi. So even the demand are also vary according to time. Okay, for four seasons countries, negara yang 4 musim, so the demand is more different. In general, relatively little water is used during winter compared to summers. So this is in 4 season countries. So how about Malaysia? Malaysia macam mana? So this is what we call demand and supply. So again, how do we control demand and supply? So we may use reservoir. okay, like a dam or smaller dams or smaller reservoir, uh, purposely for supply, for water supply. Okay, dams have many types of dams. There are a lot of types of reservoir and dams. There are dams for floods, okay, and there are also dams for managing water supply. Okay, so for this chapter is about water supply. Okay, so for reservoir, for water supply, there will be two types, like main storage reservoir and service reservoir. For example, here main storage reservoir may be located relatively distance from the customer. For example, here, okay, here is the main storage of reservoir. Okay, it's more further than the consumers. So let's say here are consumers. Okay, and there will be a service reservoir. So this might be a service reservoir. Okay, this is service reservoir, and this is a main storage reservoir. And so how it is designed, for example, the main storage may have a longer term storage. Okay, and the use of both have quite similar usage, which is to balance out fluctuations, in river flow over some period of time. Okay, so with suitable storage, the pipe leading away from the impounding storage reservoir can be designed for a nearly constant average flow. So this, for example, shown here is a storage reservoir, or we call before is main storage reservoir. So it may have some kind of pipe. Okay, where is this pipe? Here. Okay, so this pipe going out may have a constant flow. Okay, and then it will meet some service reservoir. Okay, so a smaller reservoir. Okay, before it will go to the consumers. Let's say these are all houses. So from main reservoir, storage reservoir, to service reservoir, to consumers. Okay, service reservoir normally contains up to 1 day storage, okay, and may be used to balance the fluctuation in the demand. Again, so functions of water supply reservoir is to balance the fluctuation in demand and supply. So try and think, can you identify any reservoir nearest to your home? Just think whether there is some service reservoir near to your home, or there is a bigger reservoir or dam. So that would be quite a good way to relate to this chapter in your life. Okay, so in a reservoir, okay, you should be also familiar with this kind of diagram. It's in previous chapters also. So you have a spillway here, and then you have a sluice way. So all of these are how do we draw out the water out from the reservoir. Okay, and of course, according to the storage, there are also many types of zones. Okay, there are dead storage, there are active storage, which varies. The level will vary. This active storage, and some also reservoir, although it is for water supply, it can be also used for flood control storage. So some reservoir have also flood control storage, some additional surcharge storage. Okay, so this is zones of storage in a reservoir. Okay, again, this describe more. Okay, it's the same thing with the previous slides. There are normal pool level or active storage, minimum pool level, useful storage, surcharge storage, and also dead storage. Okay, now we need to think about the storage capacity for reservoir used for water supply. So what is the storage capacity suitable for the demand in a certain location? We need to identify how much runoff or water going inside the reservoir, and how much demand or here we also call it as draw off. Draw off is same as demand. Draw off is you draw out the water. Okay, runoff is the runoff coming into the reservoir. So draw off is how much water are drawn out from the reservoir. So these are some of the designs that as engineers, as civil engineers, we need to do. Okay, to identify the storage capacity. Okay, so how do we do that? Is we can use mass curve. If you remember in precipitation, in rainfall, in the I think chapter 2 maybe, you use mass curve for rainfall. For water storage, we can also use mass curve. Okay, so a mass curve of supply is a curve showing the total cumulative volume entering a reservoir site over a certain time period. Okay, but for this case, usually years, usually a longer time of time period. So it's quite the same with the precipitation mass curve. Okay, so basically, for example, you have a hydrograph, and this is a single hydrograph. This is a single hydrograph, a single event hydrograph. Okay, you usually see a hydrograph like this. Okay, so how do you do the mass curve? It's just from Q, yeah, from Q. Okay, because hydrograph you measure or you observe, you get the flow. Okay, meter cube per second or meter cube per hour, and then you need to convert it into volume. Okay, after you convert to volume, you do the mass curve. So mass curve is just a cumulative of the volume, okay, of the water entering into the reservoir. So here, basically here is that is what it says. So this is mass curve from hydrograph to mass curve. Okay, it's a cumulative of the volume of water calculated from the hydrograph. Okay, so in reality, hydrographs will look like this. And there are a lot of peaks, ups and downs. So this is a longer time period. The previous slide shows you a one event of a hydrograph, but in reality, the hydrograph or the discharge records observation looks like this. A lot of peaks, ups and downs. Okay, because for a longer time period, there are a lot of ups and downs in the discharge. So for the mass curve, it will look like this. For water supply management, the mass curve would look like this because the time may be in years, a longer observation. So the mass curve would look like this. Okay, so this mass curve, so there are a lot of things that may be looked into. For example, it is to examine critical dry periods. Okay, and for example, the increments of the flow. Okay, what time is the flow sufficient and what time the flow is not enough for demand. So that is the use for mass curve. Okay, so for our case as engineer, we need to determine the maximum storage capacity. Okay, so we need to design we need to design or we need to check whether the storage is sufficient for the demand. And also the critical period. What is the critical period? Where we analyze what time the water is not sufficient. Okay, for example, for the proposed dam site, okay, this is the procedure of how we determine maximum storage and critical period. So there are some steps. So for the proposed, for example, for the proposed dam site, we need to construct a mass curve first, okay, which is the cumulative monthly flow over time, which I showed you before. Okay, and then we need to determine the slope of the cumulative draft. Okay, so draft here means demand. So draft, draw off, okay, here, draft, draw off is the same. It's the same as demand. Okay, and then there is a technique where we check whether the demand is sufficient. Not demand. The supply is sufficient according to demand. You will see later. Okay, I will show you. So this is just the written procedure. Okay, so there are no other better way than to do example. Example, it is given. Okay, the table is in the next slide. Table 1 lists the inflow. The inflow means the flow going in the reservoir. The inflow for one reservoir. So the first thing, for example, for this case, you determine the mean flow. Okay, the mean flow, we assume the draft or the demand is similar to the mean flow. Okay, and then we need to develop the mass curve, and then we can determine the storage capacity and critical period. Okay, so for this example, additional, you need to check whether if the demand or draft here, if the demand or draft of 75% of the mean flow, then how will the supply change, whether the supply meets demand or not. Or for this case, we just want to estimate the storage capacity and critical period. Okay, so the inflow, okay, the inflow here is given. So because it is water supply, so the Q, the inflow is in a month, in month. You see, usually it's in like every 1 hour or every 2 hours, right, before. But now for water demand and supply, the inflow, the record, the data that we need is in month. Okay, because it's a longer period of observation. So for example, in each month, how much inflow are there? Okay, so this shows the data. Okay, so what you do, because the example wants you to get the mean flow as the draft, the mean flow as the demand. So you calculate the mean, just add everything, okay, add everything and divide by the number of months, number of observation. So here you get 9.3. So this is the mean flow. Okay, so because the example told you that the mean flow is similar as demand, so here we have the inflow, and here we have the demand, or draft. Here it puts as RT. Okay, and the inflow is QT. Okay, so the mass curve would look like this. Okay, here I forgot to mention before, this is the cumulative, and because mass curve, remember, is the cumulative. And here it didn't use the volume. Okay, it still uses the Q, the flow. So it is it's all right. It's okay. You can use Q also for mass curve. You don't need to convert it to a volume. So for this example, it is still in Q. Okay. And then you cumulative it, it becomes a mass curve. So when you plot it, it will look like this. So this is time, months, and Y is the Q. Okay, so okay, remember you have the draft, the RT, yeah, the demand, this one. So this also you need to accumulate. Yeah, you need to accumulate. So once you accumulate it, it will become this kind of a line. You see it? Oops, the dotted line. Okay, so the dotted line is the demand, the demand line. So what you do for this, so this is the demand line. Why this? Okay, so this is demand line. So what you do is you superimpose. Okay, you move this line. Okay, see, you move this line at the peak of peak lines. Like here, there's 1, 2, 3, peak, peak and what, drop, peak and draft below. Okay, so put the line, put the demand line. You see these red lines are demand lines. So 1, 2, 3 and 4. Okay, so from this you can see, okay, for here, where is the spill? Yeah, the spill means, okay, the spill means there are excess of water. Okay, and you have some not spill, but because the demand line is here, okay, the red line is demand line, So you compare the demand line, for example here and here. Okay, so the difference here, the difference is the required storage. Okay, the maximum difference here. I will, okay, let's clear this up. Clear this up. So, okay, this is the maximum difference between the highest peak and lowest peak here. So this is the required storage. Okay, so in summary, this is the demand line. So you move the demand line at each peak. Okay, this is the technique developed for identifying the maximum storage capacity. Okay, and another thing is the critical period here. So you have this, because this is the maximum storage needed, the maximum deficit. This is the maximum deficit. So the critical period will be this period from the peak to the highest peak to the lowest peak here. So for here, from 36-month inflow draft record, the maximum storage capacity is 125. So this is the distance. This one, okay, this one. Okay, and the critical period is 16 months. So this is how you identify from the mass curve, the maximum storage capacity and the critical period. So what if the demand is different? For example, here it says 75% of the mean flow is the draft. Draft is demand. So this will change. Okay, this dotted line, the demand line will change. So if the demand line changes, it may also change the this gap. So this may also be changed. So it depends on the demand line. So your storage capacity will be different. Okay, beside mass curve, there are also alternative method where for this method, it compares between supply and demand on a monthly basis according to the deficits or excess. So these two words, deficits and excess. So these two words is important. So another more simpler method is you look at the supply and demand on a monthly basis and you calculate the excess and deficit. So we will look into this example. So again here you have a supply. So supply is the inflow going in, okay? Inflow going into the reservoir. And you also have demand. So demand is the demand of water needed in a certain population which uses the water supply from the reservoir. Okay, so demand values, how you calculate demand values is actually from the population numbers. There are ways to measure the demand actually. Okay, and the supply, where you get it, you get it from the inflow, okay, or hydrograph going into the reservoir. So this is the data, okay, similar with example before, but here you don't do the mass curve. Okay, you do not do the mass curve. You just compare the supply and demand, okay, and convert it into excess and deficit. Okay, so we look into this. Okay, so the excess and deficits is calculated monthly. Okay, monthly. So you have the supply record, you have the demand record. So what you do is just minus. You minus supply and demand. 8.8 minus 72. So if it is negative, okay, then you call it as deficit. And deficits means it's not enough. Negative values. Okay, if you, okay, let's say, okay, here the supply is larger than the demand, okay, so it is a positive number. Here also is larger than the demand. So when it's positive, you put it as excess. Okay, okay, and you can also calculate cumulative here. For example, here you just cumulate what you get. But once it becomes positive, you can see that it is full. Okay, it's positive, you can say that it is full. Okay, so the important thing is you see here, okay, the deficit, the excess, okay, the deficit time, the excess time. Okay, so how you do this is just supply just minus demand. Okay, so what is the storage capacity required is you just take the highest deficit. So this is the highest deficit. Let me clear this up. So the highest deficit is here. Okay, it's here, 264.8. So you can say that the storage capacity required is 264.8. Okay, and also you can see the first spill here. Okay, here 535 excess minus 116. So 419 is the first spill. Okay, and then second spill is 314 minus 264. 314 minus 264. So this is another method which is I think normally used also. So you need to try it. You need to understand this one. Okay, so we completed on how do we calculate the storage capacity, okay, and the critical time, critical period. So now there is another thing that you can do is you can identify the wait, the probabilities, okay, certain events, okay, the probabilities of how much volumes of runoff, okay, are usually there in a certain river going into the reservoir. So you can do this by using a runoff accumulation time frequency diagram. So this is quite similar with frequency analysis. In the previous chapter is on rainfall frequency analysis, but here it is for a flow. Okay, you can identify how much percentage of probability is this flow. uh, the values of remember the values of flow are different, okay, according to time. So we can also calculate which has the highest percentage of flow, the value of flow, how much has the highest probability or highest percentage. Okay, so another word is called flow duration curve. So it shows the proportion of time during which the discharge that equals or exceeds certain values. So this is quite similar with frequency analysis, but it is more simpler. Okay, and here it's also need to understand area under the curve represents volume. Okay, so here you see different from frequency analysis for rainfall. This one, the x-axis, you can see as a percentage. Okay, and then the y-axis is the discharge. Okay, for example, discharge is equal to or greater than 2000 meter cube per second. Here 2, okay, because it's the unit is kilometer cube per second. This is not kilometer cube per second. It is kilometer cube per second. So and this is 2000 meter cube per second. Okay, so the percentage is here around 70%. So we can say the discharge is equal to or greater than 2000 meter cube per second for 17% of the time. Okay, so this is just to see the distribution of the values of the flow, okay, in a river. Okay, so how do you do this? How do you do the flow duration curve? Is one, first you need to make it into class intervals because this is a more simpler way of frequency analysis. It is not a continuous distribution. It is a discrete distribution. So you have to make it into class intervals. Okay, and then you need to count the number of occurrence. Okay, frequency, the frequency of each class interval. And then you accumulate, okay, you accumulate the frequencies beginning with the largest discharge, and then it is expressed as a percentage. Okay, and then you just plot the accumulated percentage in a normal graph, or it can be in a probability, a log normal paper. Okay, but now we have Excel, so you can just do it in Excel. Okay, again, so this is just to show that in a long time, the discharge varies, varies according to time. So what is the probability, how much percentage is the discharge, let's say this values and this value, this line. So how many times this value occurs. So for example, it occurs like this and here and this point and this point. So this is the frequency, okay, how many times it occurs. And for example, we have another line here. Let's say this value. So how many times it occurs? 1, 2, 3, 4, 5. Okay, sorry for this really rough sketch, but I hope you understand. So we calculate the frequencies of the flow. Okay, how many times it occurs? How many times a certain value occurs? Okay, so this again, this is here is the step procedure here. Here is the procedure. So first you group it into classes, and then you calculate how many times this class, this value occur. Okay, and then you just cumulate it, and then make it into a cumulative frequency. So how do you do that? It's just okay, frequency, cumulative frequency is just you divide 3, for example 3 over 1461, so you get 0.21%. 3 divided by 1461 multiplied by 100, so this is how you get 0.21%. So you can test, try and calculate whether this is correct or not. Okay, so then according to the percentage, okay, you can just plot this. So it become a flow duration curve. Okay, so this is the same example as I showed you before. Okay, so the example is actually a 4 years period. So it has 1461 days. That's why you divide by 1461 days. You want to get the percentage of the occurrence. So we can say that 2% of the 4 years period, the flow exceed 290 meter cube per second. And we can also say that for a 3% to 96% of 4 years, the flow is between 12 to 290. So you can check this with the graph that were developed. Okay. And also 50% time point provides the median value. Okay, 50%, which is the highest, not highest, the middle. Okay, so this is the median value, which is 45 meter cube per second. Okay, so what else can we use using this flow duration curve? So this is important. For example, the low flow. Okay, for example, 90% to 99%. So this area, okay, 99%. So this is, we can say this is the low flow. Okay, you see the low flow condition here. So at this time, low flow is critical. Okay, so this is how engineers or designers estimate the extreme cases. For example, the low flow. So this is the risk. The risk exerted for the reservoir, whether the flow will be enough going inside the reservoir, and for the demand. So here 90% of time discharge exceeded. 90% of time discharge exceeded. So 90% is 90%. Okay. So more than this, let's say 50. So more than 50. A measure of groundwater and riverbank storage contribution to stream flow. Okay, and what else? Used to estimate hydropower potential for water supply and irrigation planning. So this because, let's say, we need a flow of 200, okay, in order for the hydropower. But how many percentage? is the flow 200. So let's say this is only 10%. Okay, 10% of the time the flow is larger than 200. So it's not really that good. So this is how you use the information for flow duration curves to decide for decision. Okay, so the steepness of the slope also shows you something. The steeper the slope, the greater the variability. If the slope of the curve in low flow portion is flat, so this shows that groundwater contribution is significant. Okay, and if it's steep curve, poor base flow or cis2 flow condition. So this is a valuable tool for comparing basic characteristic of the catchment area, in particular the geology groundwater. So these are kinds of different type of slopes. Okay, so it's not really complete if you don't have an assignment. So for example, for this chapter 9 assignment, okay, table Q1 in the next slide, this is the mean monthly flow of a river at Sungai Muar Johor. So do the flow duration curve, okay, using Excel, okay, and then determine the flow rates for 5% and 95%, okay. So this would be your assignment. So the steps, remember, the first step is you need to do the what class, you need to do the class, column 1 classes, and then you need to do the frequency, okay, calculate how many times this flow occur, and then do the cumulative of frequency, and then do the percentage. So and then you plot the graph. So you plot the graph, then you can see for 5% and 90% what is the flow rate. So good luck for this assignment. Okay, and just for activity, so this is for maybe power okay, power plant, you can say power plant. So you can calculate the power, okay, but you have this, and you will given this kind of formula, so the relationship between P and Q. So do the same thing, flow duration curve, you just need to convert P to Q. So this will be an activity. Okay, this is not an assignment, it's just an activity. So you finish chapter 9. Okay, so this is the second last. So the next chapter will be chapter 10, your last chapter for hydrology. So thank you very much.